check the screen. Actually, okay. Checking the screen. Audio doesn't seem to be working, or does it? Let me check another way. Okay, it's working on my iPhone. It's not working on the computer over here, but that's okay. Maybe it's working on it. It is working. Okay. All right, so we started in on chapter 4, and we started with this cross product. So what I'm going to do, I'm going to dig straight in. So what you read about the products of them, one thing that's interesting is that if you cross two vectors one way, you cross them in the opposite direction, you get the negative vector. There is something else that's very, very interesting here, and it's used a lot in dynamics. That is, if you cross these two vectors, they are both 90 degrees to each other. So in other words, C is perpendicular to A, and C is also perpendicular to B. The reason that's so advantageous is by rule, by law, whatever you want to call it, A dotted with C is going to be 0. Why? Because magnitude of A, magnitude of C, cosine, the angle between them becomes 0. This is very handy later on in dynamics. So in other words, C dot A, C dot B, both of those are 0. So that's something to to be mindful of. I do not think that he talks about that here, but he talks about a lot of this other stuff. He talks about how to do the cofactor expansion. You cross these out and take this matrix, cross this out, you have to make sure you have a minus sign. You do a cofactor of here, cross these out, and you're cofactoring there. So let's just, okay, here he's talking about a moment vector. If you have a vector from a location to the point of the application of a load, if you take this vector, crossed it with that one, you would get the moment, R cross F. So let's head off and go work a problem. He has some of them worked here. I'm going to go ahead and find some other ones down in here. He's added these sections which are very, I don't like the preliminary problems. just take, I don't know, these are fairly simple, but here we go. So, here we'll go through and find the moment about a point O. So I simply do this. Point of application of the load is right there. So what I'm going to do, draw an R vector. R is pretty easy, given the fact this is X, so this is Y. You would have 5I plus 2J, and then you take the force vector and 4/5 of the 100 runs along the X. I'm going to go ahead and then 3/5 run. Now you have to remember, running this direction right here. You have a vector that's running this direction and it's running that direction. Positive, negative. 100 times 3/5 J. So now, if I want to find a moment, I would just simply line these up. Now, if I want to do this, this will give me 20, and that'll give me 80I minus 20 will give me 60J. Okay, I, J, K, we move this over. And let me back this up a little bit. R cross F, and just to double check, we run back here. Just the simple, I guess I could have stopped there and done it there, but let's go back to the simple definition. I could have done it here, but here's what we're looking at. It's always R cross F. Okay, head off back to the problem. So we list R first, I, J, K. We list the other one second, 80 minus 60, 0. Now, and this is supposed to be equal, so if we just carry this out, cofactor expansion, removing this and this, and taking this over here, we get 2, 0, minus 60, 0. Now, I'm going to list them below it, taking the cofactor expansion, taking this one out, and this one, taking the matrix as this, and listing it here, 5, 80, 0, and 0. And then doing the K, and doing the cofactor expansion, taking that row out, taking that, taking this matrix, sticking it in here, 5, 2, 80, minus 60. What is interesting, that's going to yield you 0, that's going to yield you 0, that's going to yield you 0, that's going to give you 0. The only thing you're going to get out of here is the K component, 5, 2, 80, minus 60. It's going to give you here minus 5 times 60 minus 2 times 80. So it will be equal to minus 2 times 80 minus 5 times 60 K. So minus 160 minus 300 minus 460 K. And I believe that's the correct answer, but let's double check. This is the first one. in this sequence, meaning it is, I'm going to have to run backwards. Now what I'm going to do with this problem is I am not going to call it quits here. I'm going to do something interesting. Okay, back to the F. So he says minus 460. Now, this is the case. Okay, so if you take I and cross it, take your fingers and point here, come across to here, what you're going to get is a vector that comes towards you. Your thumb will come straight up at you. That indicates that curling your fingers in a counterclockwise direction is positive. This indicates that it curls the other direction or that it goes this way. Now, I'm going to do something kind of interesting. Now that we have the answer, we could stop here, or I could use this case, use this example to show a couple of other interesting aspects here. Let's do a couple of things, but I guess I would have to remove a lot of this information, or maybe I can just copy it into a different direction here. Here's what I'll do. Okay, I'm just going to copy the picture, or you know what, I'll go back and get the picture, but I will not get the text around the picture. Because now I'm going to use this problem to show some interesting things that are in the textbook, but it's best, I think, to actually, so there. Then take the same problem, put the picture about right here. Now we know this is the answer. Okay, so we know this is the answer. So here we go. Here's our answer. What else can we do? Well, let's try something very, very interesting. Okay, and I'm going to bring out my ruler, and I'm going to take my time here. Now, looks like, now I would not say I believe this, but here's what I'm going to do. Well, let me run it backwards the other way as well. So here, just take this line of action. So I'm going to call this the line of action, so to speak. So let's say I did something really weird. I took this 100 and I'm trying to draw this over the top of it. And what I'm going to do, I'm going to take this thing, I'm going to drop it to the point that it's right here. And I'm going to get rid of my ruler because I'm sort of rough-handing it a little bit. And I'm going to say, this is where, actually, let me do a different color here. What? Okay, wait. Erase that. Don't tell me I've got stuck in this mode again. All right. Give it a second. Oh no. Oh, fine. Okay. So here we go. I'm going to say, I'm going to move this along its line of action, and then I'm just going to arbitrarily move it down here. First question is, how far? That doesn't look good. So The question I'm basically saying is, how far is this? If I'm moving it along the line of action, I moved it down 2. So if I moved it down 2, so here's what I'm saying. I'm not necessarily interested in what's the distance from here to here because it's 2. But if I took this and moved it down 2, how far did I move it over? Well, if I moved it down 3, it would have been 4. So again, if this were 3, this would be 4. But it's not 3, it's 2, which I just wrote over that. So, in fact, it's 4 times 2/3, which do I have? Okay. Or 2.6667 and whatever. Now, what I'm going to do is I'm going to try something really interesting. If I took the point of application of this load and moved it from this point to that point, what would the moment be? So now I have to draw my vector from here to here. This is my new R vector. My R is now, okay, 5 in this, it would be 7.6667I plus no J, and plus, of course, no K. And because of that, I'm just going to take this off. And now I'm going to say, what's the moment due to this load? R cross F. Now, my F is still the same thing. And so now I'm just going to go up here and say, my F remains the same, and it's 80I minus 60J. That comes from right up here. So I'll keep that kind of here, and I actually may just move it down because it's up in the other area. So I'm going to just move it down. So now we got hang on. We got the I, the J, the K. Now I got 7.6667, and I don't know. And now my F is going to be 80. Okay. And then the minus 60. And then the nothing. Now, generalization. Here's the key. Okay. Any matrix I have, if I have this right here and this here, 2 zeros, I will never have these 2 zeros end up here, and they end up here, meaning I'll never have an I, never have an I, and never have a J. So I can just go straight to the K if I want to. And if I go straight to the K, I will end up with K times 7.666. I don't know how many times you want to repeat that. 80 minus 60. Of course, this will give you a number which will be minus 7.666 times 60, and then this will give you nothing. So let's take a look, and let's just okay, here's what we'll do. Parentheses 5 plus times 60, 460 minus 460. So the moment is equal to minus 460K. Interesting. Have we seen that before? And in fact, we have. Now, let's even do something even more bizarre. Okay. What we'll do, take the same picture, copy, and actually, maybe I want to take more than just the picture. Tell you what I want to do here. Hang on. I want to take out this, and what I can do is copy this and then eliminate part of it from the copy. Okay, now I'm going to do a copy of this. Hopefully I got what I wanted out of it. I'll drop it back down here. Okay, now instead of copying this vector here, okay, I'm going to do something a little bit weird. I'm going to basically look at this, and I am going to copy this vector, which was right here. This time, I'm going to put it right back here. Now the question is, okay, just like before, what's the vector that points to yuck? Okay, anyway, try this again with this one. All right, well, here. What's the vector that points here? Well, first of all, this distance is 2. What's the distance here? Well, this moves 5. Now, if this were 5, but it's not, sorry, I spoke differently. If this were 4, let me move this R over here. If this were 4, this would be 3. It's not 4, it's 5. So, what you have to, I'm having trouble with my pen here. What you have to do is that it's 5 now, but if it were 4, it'd be 3, so 3/4. So in other words, if this were 4, this would be 4, and then that would be 3. So it's not, so you get that being the distance. So this means my R vector in this particular case would be nothing times I plus, okay, I might as well be precise here, 3.75. Okay, so this is 3.75. Add that to 2 would be 5.75 times J. Now, I want to find my moment due to the load that was put right there. And it turns out the load itself never changed, so I can just copy it and I can drop in here and say it's here. I'll draw this and just put it right here. So this force is still that. Moment is R cross F, which is I, J, K. Put the R in here now. It's 5.75 and nothing. And then I still put my 80. I still put my minus 60. Still put my nothing. Now, again, the fact that this is in here means there's no I or J component. So I can head off and just say, well, my K component is going to be 5.75, 80, and minus 60. Okay, that's nothing. This, since it's in the opposite direction, will be minus. So remember, you do plus this way and minus this way. 5.75 times 80. Oops, 80. Okay. 5.75 times 80 is 460 minus 460, and that's okay. So my moment in this case is 460. That's the same thing that happens there. So what does this mean? This means there is a rule in the book that I skipped over, but now I have kind of proven. Let me see if I can find it. It's the one. It may be in this section, it may be in the next section. Okay, principles of transmissibility. Here it is. So what does this mean? So you've seen this in action now. You take a force, you have a line of action. You can move this force anywhere as long as it's along the line of that action. You can move it to here, to where the R draws. What I like to say is it draws to the base of the force. You can move it to here, which means it's drawn to right there. You can move it back to here. You get the same moment regardless, as long as that F is transmitted along the line of action. So let's review what we did. In the first one, we just solved it, right? It was just there. Then what we did is we found the line of action and we moved it to a point which was kind of out here, but it was still just moved directly along the line of action. We got the same answer. Then we decided to move it all the way back to the base. Same line of action. It's along the line of action. So as a matter of fact, we can make the math harder by arbitrarily putting this force anywhere. This force can be moved anywhere along the line of this action. It will still result in the same moment regardless. Now if you put it here, what happens to your force, your R vector? It goes to here. There's your R. If I move it somewhere else, so if I move it up to, say, here, for example, and guess what happens is that vector R goes to the point of application here, and that's your cross product. Turns out it still comes up with minus 460K. So the point is, I can move this force anywhere. I'm not sure. Yeah, I put it right there in this example. I can move it anywhere. It will still come up with the same answer. So if you see an opportunity to, say, find out a location that is more convenient for quickly calculating things, then yeah, go for that. Now, let's go one step further. Why would you want to do that? Here, let me give you a case in point. Let's stare at this one for a minute. Okay, let's try to see if we can find out a justification for simplifying things. Okay, I'll use this color. So now what we've got in this vector is that this is 80 and this value is the 60. Now, let's take a look at this. Let's simplify this. Here we have our base. This is point O. We have a vector going out here to here. We have a force 80. And we have this force, or say here, we have a force this way of 60. Since that's going directly at O, this produces no moment about O. It's just pushing against O. So in other words, this force produces no moment because its moment arm does not exist. Now let's look at this one. This distance right here is 5 5.75. This is a moment, which is 80 times 5.75. 80 is the force, moment arm is 5.75, and it happens to be creating a moment in that way. In other words, this is going around that in that way. Guess what? Here's your X, here's your Y, here's your positive moment. So this means this direction is a negative moment. It's negative, indicating that in fact the moment is this way. Now, let's see this from the other example. I think it's up here. The other example is I placed it here. I think this was 2.6667. Now, let's take this case in point. What we have is we have point O. So point O is right here. We have a straight out to the right. This is this point right here. I have a force that is going 80 to the right, and it's going 60 down. This is a total distance of 7.6667. I don't know how many times you want to do it. This one produces no moment about O here. Well, let's take a look at it. Here's your 80. Here's your moment arm. Produces no moment. Okay, this one is 60. Here's your moment arm. Here's your 60. Here's your moment arm. It's producing a moment in this direction. In other words, if you look at this, this rotates around this way. Again, X, Y. This is a positive moment. Obviously, I've got a negative moment. Answer comes out as negative, indicating that I've got this orientation or a clockwise movement. Here's your clockwise movement. Now, these are two cases that are simple in the fact that it just so happens I lined up the coordinates. So this one produced no moment here, and this one produced no moment here. If you were somewhere in between, both of them would produce a moment. You'd have more complicated results. So there could be a case in which, say, someone had an object and say they had a line of action so that you could easily determine, okay, that's supposed to be a straight line. So you could easily determine the distance right here. Okay, so if that's the case and you had this broken down so that you knew that this was, say, 10, and due to the geometry here, you just knew that this was 10, and say this was, 50, or that's not the scale, so let's maybe make it 7. Then in fact, you could say, hey, I'm going to do this. I'm going to transfer this back to here. And then what's my answer? My moment is simply 10, or this 10, times the moment arm of 10. And it's producing it in this direction. And so that's what they'll do sometimes, is they'll put, or they'll say 100, and like this. In the book, sometimes they won't put a plus or minus here. They'll put the value and then the moment direction. So in this case, you quickly moved it along the line of action. You found out through geometry that this is, say, 10 right here. And it could be anything. It doesn't have to be equal to this. But it turns out you made this quick analysis without doing the cross products. So that's kind of beneficial sometimes with transmissibility like that. Let's see. Here he talks about the direction, the magnitude. I'm just trying to see if I covered, but that's a case in point if you want to look back at that and rewind and think about what that is. But if you are kind of having trouble, here's a good case where everything is carried together. You know, he drew your RA up to this point A, then he found the vector which drew itself from A to B. So again, the way I like to do things is, you know, I go down 12. Now I have made mistakes on this before. Go out this way and this way to get to this tractor. You're going 4 meters in the X, you're going 12 meters in the Y, and you're going down 12 meters in the J. I mean in the K, sorry. So he's got this, divides it by the length. He actually now has the force vector here. Now what can he do? The force is applied at A, takes that vector. Wait a minute, here's your RA. I don't know what that little thing, those things are, but it's 12K, so what you notice, you get nothing, nothing, and it's 12, meaning the vector is like from the base of the tree to the top. Then he takes the vector, which he found a minute ago, sticks it straight in here, and he gets the moment. So in fact, what you find out is that O, I'm not sure, maybe he draws it. Yeah, he draws it. So here's your plane. Now here's this is something you can take a look at. You can prove it to yourself. Yeah, okay, hang on. If you take, okay, it's not necessary here, but it's very beneficial in dynamics for at a certain point. You're taking this vector and taking that vector. And what I'm going to do is take this, put it, oh, I copied both of them. Oh well. Anyway, in other words, this F vector, so this is perpendicular. Ooh, this is not looking very happy. These two vectors are perpendicular. In other words, the resulting moment, if you want to be able to check, has to be equal to 0. Let's take a quick look at this. This is just a check. This is not, you know, a given here. So if we're taking this, and I don't like the way he's doing this here. As a matter of fact, I don't like this at all. So let's go back to this, and I take the resulting vector. So let's ignore this, and I'm going to say the moment 0 cross with RA. Okay, let's take a look at it. This number times that number plus this number times that number. I think by nature that's 0. So I didn't really get much out of that one. But now let's take this, all M moment resulting times I'm sorry, I should have been saying dotted with. I'm dotting this, okay, I retract what I said. I'm dotting it. So now I'm going to take this number times that number plus this number times that number plus 0K times that number. Let's see. Uh-oh, wrong place. Okay, so I'm going to take this, I'm going to take minus 16.5 times 0.4588. Now, one of the things is there's probably extra decimal spots here. But here you go, minus 7.57. Now let's look at this. 5.51 times 1.376. And you get pretty much close to the same thing. Now, if you carried out all the digits here, and here, and here, and here, you should find that this number times that, added with this one, they should exactly equal 0. So this is a way to check your answer, is you dot it back with the 2 rows here. Dot it with this one and dot it with this one. You might as well get used to this. This is a check that I use in dynamics. Why do I not like this one? And here's the reason I don't like this one. Is because, now, it is true, what he's saying is true, but I don't like it because he's drawn it as though the force existed right here, and the vector is drawn to right here. Now, what he didn't do is he didn't use his words there to say the lines of transmissibility are such that I can take this force and I can transmit it along its line of action to where the tractor is pulling. Okay, I'm not doing a good job of, okay. So now the dude is down here pulling on this tractor. So he didn't use or, and this is why. So why can you do this? Because this vector now draws to the tractor, the guy on the tractor, and transmissibility says I can just take that force, and as long as it's in the line of action, I can copy it down here. Now, carrying out that process, you get the same answer. But I'm not sure, maybe you could read in the text, but I don't think he actually used his words. He just said or, and basically said, or you figure out why that I can do this and I get the same answer. He should have said something about transmissibility there. I see no words written here to describe as to why, and so that's the reason I don't like that. You should have used those words to say I'm transmitting it down there along the line of action. Okay, this is principles of moments. You know, all he's doing here is he's saying this. If I broke this down, this is weird. Okay, so I can break this force into 2 forces. And once they're independently broken apart, this is weird, but here, let me do each one individually. Go away. So I'm going to copy this one. I'm going to say now I no longer have this one. I have 2 of the others. And I am going to move this along its line of action, which will be right there. Yeah, you get the point. And then I got another one that I'm going to draw along its line of action. Transmissibility down its line of action puts it right here. So what does that mean? That means this is x times fy, and this is fx times y. And so this will produce a moment this way. This one will produce a moment that way. So they're both going in opposite directions. Depends on which way you want it to be described. But guess what you get? Fx times y. And it's positive. Think about this. This is actually positive. So the question I have is the sign convention correct with respect to this, or are you just keeping up with it? In this particular case, I think you're keeping up with it, because here's fy times x, and so what you can do So you can break a force into components and move those components along their line of action. Oh, word of the day, and then we'll go. This is static content. And pen, we'll just use the word pen. And I think at the end of this, and it's done, and it's done. We'll call it good.